Hey everyone, and welcome back to our series on post quantum cryptography. I'm Survi Singh, Senior Consultant at Encryption Consulting, and today we're going to be focusing on understanding the PQC algorithms that NIST has approved for standardization. Since there's a lot to cover, we've split this video into two parts. In the first session, we're covering the core standards ML-KEM for secure key exchange and ML-DSA for digital signatures. Then, in part 2, which is coming out very soon, we'll explore the important alternatives SLH-DSA and the new backup key mechanism HQC. NIST's work is constantly moving forward, so as new developments happen, like the future standardization of algorithms such as FNDSA, we'll be sure to cover those updates in our future videos. Make sure to follow us to stay completely up to date with all of the latest progress. And finally, we've attached more resources for you in the description, so be sure to check them out. Here's everything we would be covering in our two-part series. We'll begin with a brief overview of the NIST PQC standardization project to set the stage for why these new algorithms are necessary. Next, we'll cover the three foundational Federal Information Processing Standards or FIPS that govern the new PQC schemes. These define the primary key exchange and digital signature algorithms. Following that, we'll specifically discuss HQC, which serves as a critical diverse backup algorithm in the PQC family. Finally, we'll bring it all together with the user matrix. This is the most practical part of the presentation where we'll show you exactly which algorithm to choose based on your specific needs for speed, size, and security. We'll conclude with a brief section on how our team of experts can assist you with the PQC migration. Now that we know our roadmap, let's start with our first topic and understand the why behind the NIST PQC standardization effort. In our previous videos, we've talked about the threat of quantum computing and the need for new security standards. But how do we get there? The answer is the NIST Post-Quantum Cryptography Standardization Project. This isn't a small effort. It's a massive global multi-year initiative led by the National Institute of Standards and Technology. Its single goal is to find and standardize new cryptographic algorithms that can protect our digital world not just against today's threat, but also against the powerful quantum computers of the future. This wasn't a quick process. It began back in 2016 when NIST issued a public call to cryptographers and researchers around the world. The response was overwhelming. In 2017, they received an astonishing 82 algorithm submissions from 25 different countries. They kicked off a rigorous multi-round evaluation process where submissions were subjected to intense analysis. Over the next few years, from 2019 to 2022, the submissions were carefully evaluated and the field was narrowed down to a set of finalists and alternate candidates. NIST and the global cryptographic community worked together, testing, scrutinizing, and providing public feedback to find the best of the best. This long and careful process reached a major milestone in August 2024 when NIST officially published the first three final standards. This marked the completion of the first and most important critical phase of the project. But the work isn't over. The project is still ongoing, with NIST continuing to evaluate additional algorithms. This ensures that we build a diverse and robust portfolio of cryptographic solutions, guaranteeing our security no matter what the future holds. After years of rigorous evaluation, testing, and public scrutiny, the NIST Post-Quantum Cryptography project reached its first major milestone with the initial set of standards finalized in 2024. But the most important takeaway isn't just the names of the algorithms, it's the strategy behind their selection. NIST didn't put all of its eggs in one basket. They purposefully chose a portfolio of algorithms based on different mathematical foundations. This is a critical risk mitigation strategy, ensuring that if a single vulnerability were ever found in one type of math, it wouldn't compromise our entire digital security system. It's the cryptographic equivalent of a diversified financial portfolio. The initial three finalized standards are the cornerstone of our migration strategy, and there are more standards currently under review or in development. First, we have FIPS 203, which standardizes ML-KEM. This is a primary lattice-based key encapsulation mechanism for general encryption. Think of this as the go-to standard for securing data at rest and in transit. Second, we have FIPS 204, which standardizes ML-DSA. This is a primary lattice-based digital signature algorithm. This is the workhorse for authenticating a document's origin and ensuring its integrity. And finally, we have FIPS 205, which standardizes SLH-DSA. This is a hash-based digital signature algorithm. Unlike the other two, it's based on a completely different kind of math. This shows this as a powerful backup, providing a crucial second line of defense if a weakness is ever found in lattice-based signatures. To bring all of this together, let's take a quick look at the portfolio of algorithms that NIST has developed and standardized. You can think of these as the fundamental building blocks of a quantum-safe future. First, we have ML-KEM, which is defined in FIPS 203. This is a key encapsulation mechanism, or KEM. What that means is it's the primary algorithm for a secure key exchange, allowing two parties to establish a secret key that they can then use for encrypted communication. It's built on a lattice-based mathematical foundation, which gives it two key features. It's incredibly fast and it produces very compact keys and ciphertext. This makes it the ideal general-purpose standard for securing data in transit and at rest. Next is ML-DSA, defined in FIPS 204. This is a primary digital signature algorithm. Think of this as the modern quantum-safe way to verify a digital document's authenticity and integrity. It's also based on lattices and is designed to be the main workhorse for general-purpose digital signatures. Its key feature is a great balance of speed and performance with a moderate size for its keys and signatures, making it a powerful and efficient choice. Then we have SLH-DSA defined in FIPS 205. This is another digital signature algorithm, but it's a strategic alternative. It's unique because its security relies on the well-understood and proven strength of cryptographic hash functions. This provides a major benefit for long-term confidence and makes it the ideal choice for high-assurance, long-lived signatures. A key feature is that it's completely stateless, which means you don't have to keep track of anything between signatures. This simplifies management and makes it highly scalable for large-scale applications. Now, for a couple of important ones in the portfolio, we have FNDSA, which is in draft as FIPS 206. It's another lattice-based signature algorithm, but it's specifically designed for specialized constrained environments. Its key feature is that it produces the smallest signatures amongst all of the approved algorithms, making it perfect for things like IoT devices and other hardware with limited memory and processing power. And finally, we have HQC. This is a key encapsulation mechanism that is currently under review. Its security is based on a completely different mathematical field, error correcting codes. This makes HQC the crucial backup plan for ML-KEM, ensuring cryptographic diversity and long-term security if any vulnerabilities are ever found in lattice-based cryptography. We will be breaking them down in more detail in the upcoming slides. With the project overview complete, it's time to look at the first core standard. We're starting with FIPS 203 and the primary key encapsulation mechanism, ML-KEM. All right, let's start with the most critical piece of the PQC puzzle, FIPS 203. This is the standard that introduces ML-KEM, our key encapsulation mechanism. Think of ML-KEM as the absolute go-to algorithm for key exchange. Its job is simple. Securely protect the secret keys we use for encryption against any future quantum computer attacks. It's the official replacement for everything we currently use to start a secure connection, like old RSA and ECDH. The process itself is clearly defined by the standard revolving around three simple steps: key generation, encapsulation, and decapsulation. That's how we establish a quantum safe connection. From a management perspective, ML-KEM is great because it's scalable and has a strong security strength. We aren't locked into one security level. NIST gives us three options: ML-KEM 512, 768, and 1024. so we can match the security strength to our exact needs. And the general recommendation, start with ML-KEM 768 as it gives you the best balance of strong security and performance. Finally, for our development teams, the standard is designed for easy integration. It uses a fixed 256-bit shared secret key and comes with a clear defined API. This means integrating ML-KEM into your existing system is made much more straightforward, reducing the headache and effort required for the migration. We are now examining the strategic design of ML-KEM, our new primary encryption standard standardized in FIPS 203. It is not built as a single opaque formula but as a highly organized system using 6 specialized components. This deliberate modularity ensures robust security, simplified development, and reliable performance across your enterprise. Our security starts with certainty. ML-KEM relies on the established and globally vetted SHA-3 family and shake functions as its cryptographic primitives. By anchoring the algorithm to this proven core, it ensures the foundation of ML-KEM is inherently secure, mitigating any risk by using mechanisms that have already passed extensive industry scrutiny. ML-KEM is designed to support your development teams directly. Complex, low-level hashing operations are abstracted behind clear high-level names, what we call wrapper functions. This standardization prevents common integration errors such as confusing bit length with byte length, making development cleaner, faster, and much more reliable. The generation of key material is handled with absolute precision. It uses specialized dedicated functions like the pseudo-random function and the extendable output function to generate all of the necessary complex randomized data. This approach ensures the key material is secure and mathematically sound, moving the critical task of randomness control into a highly governed module. The entity is the key to ML-KEM speed. This essential technique is integrated to transform the most computationally intensive operation of the polynomial multiplication into a series of simple high-speed calculations. The entity is the structural engine that guarantees ML-KEM can deliver the required high performance and minimal latency necessary for real-world application volume. Lattice-based security requires the inclusion of carefully controlled mathematical uncertainty or noise. Dedicated sampling algorithms are used to generate this necessary small, precise error and uniform random numbers. The high degree of precision in this sampling ensures the stability and cryptographic integrity of the lattice system, preventing failure while maintaining security. Finally, we ensure universal compatibility and accuracy. All data handling, including compression and encoding, is governed by strict routines that mandate the use of integer arithmetic only. This prohibition of floating point math eliminates the risk of inconsistent rounding errors across different computing platforms, guaranteeing the perfect key interoperability and cross platform reliability throughout your digital infrastructure. ML-KEM isn't a one size fits all product. It comes with 3 approved parameter sets. This flexibility is key because it lets us precisely match the security strength and the performance profile of the algorithm to the needs of a specific application. NIST designed these sets to align with the security levels we are already familiar with from traditional encryption standards like AES. The foundation level is ML-KEM 512. This is a Category 1 security which is roughly equivalent to using an AES 128 key. It provides a strong baseline level of protection. The middle tier and the one NIST recommends as the default for general use is ML-KEM 768. This aligns with Category 3, offering security comparable to AES 192. It's the sweet spot, the best balance of high security and optimized performance for most of our requirements. Finally, we have the maximum assurance tier, ML-KEM 1024, which provides Category 5 security equivalent to a 256-bit AES key. You can use this when you need the absolute strongest protection. When you choose a security level, you're making a direct trade-off with size and bandwidth. The higher the security category, the more data you have to send. For example, if you choose the default ML-KEM 768, your encapsulation key is about 1184 bytes and the secret ciphertext is around 1088 bytes. That's a moderate size that works well across most networks. But if you jump to the higher security ML-KEM 1024, those key and ciphertext sizes increases significantly. This demands more bandwidth and can introduce more latency on slower connections. This is the practical cost of the higher security. One final important detail to note is the decapsulation failure rate. Because ML-KEM uses math involving some noise, there's a theoretical chance the recipient won't correctly retrieve the secret key. But I want to emphasize that the risk is negligible. Even at the lowest 512 level, the chance of failure is so small that it's essentially zero in any real world scenario. The higher tiers simply reduce this already non existent risk even further. So the recommendation stands: use ML-KEM 768 as your reliable starting point and only move up to 1024 if your application absolutely demands the highest security level, accepting the increased bandwidth cost that comes with it. First and foremost, ML-KEM is a designated replacement for today's quantum vulnerable encryption algorithms like RSA and ECDH. Think of it as a strategic upgrade to your security infrastructure. ML-KEM is designed to be a direct drop in replacement. You don't need to rebuild your systems from the ground up. You can simply swap out the old encryption for ML-KEM. This secures your data both at rest while it's stored on a server and in transit where it moves across the network. Because it's a FIPS standard, it's a government mandate for US federal agencies and their contractors. This isn't a suggestion, it's a requirement that establishes ML-KEM as the authoritative standard for secure data exchange. Ultimately, this broadens its applicability, making it the go to standard for securing most general purpose communications and data storage worldwide. ML-KEM isn't just secure, it's also incredibly fast and efficient. This is a crucial business benefit as it means you don't have to sacrifice speed for security. The standard's design is built on structured lattice based mathematics. This unique approach results in comparatively small public keys and ciphertext. Smaller keys mean less data to transmit, which reduces your bandwidth and storage requirements. It also increases high speed by using efficient polynomial arithmetic, dramatically accelerating key generation and encryption or decryption. This ensures minimal latency for your systems. Its optimized performance makes it resource friendly and suitable for a wide range of devices, from high performance servers to low power ID gadgets. Finally, FIPS 203 was designed to make a complex cryptographic transition as simple and secure as possible for developers. The algorithm is practically deterministic, meaning it behaves predictably. This eliminates the complexity and potential errors associated with managing a decryption failure rate that can occur in other probabilistic schemes. Development is further simplified by using a fixed 256-bit shared secret key, providing a predictable and easy to manage output. The standard requires explicit validation of inputs, which enhances security and simplifies the process of ensuring a correct implementation. Finally, it provides a clean, well defined API that acts like a clear blueprint for developers. This streamlines integration into existing systems, reducing development effort and helping you get to market faster with a secure solution. We're diving into the implementation rules for FIPS 203, which governs the ML-KEM. These six requirements are essential engineering mandates that ensure the system is not only quantum safe but also resilient against practical attacks. The first rule establishes architectural boundaries. The underlying encryption scheme or Kuiper public key encryption cannot be used on its own. It must only be implemented as an internal subroutine for ML-KEM. And why is this so critical? ML-KEM adds a crucial layer of security, specifically indistinguishability under chosen ciphertext attack, which Kuiper public key encryption alone lacks. The requirement forces implementers to use the full robust scheme and not a mathematically weaker component. Next, we enforce an isolation boundary. Internal cryptographic functions are not to be publicly exposed to the application layer. The cryptographic module itself is solely responsible for generating all necessary randomness and managing the internal state. This prevents developers from accidentally bypassing the core security logic, such as misissuing a function or critically introducing an external unapproved randomness source that would entirely compromise the established secret key. This addresses the quality of our secrets. All required randomness must be generated using a NIST approved random bit generator. Crucially, the security strength of that RBG must align with the quantum security level of the chosen ML-KEM parameter set. For example, if you implement the Category 3 scheme, ML-KEM 768, your RBG must have a security strength of at least 192 bits. This ensures the established session key is derived from high quality entropy with the system's claimed security level. Requirement 4 is a direct defense against side channel attack, data destruction, or zeroization. All sensitive intermediate values, temporary key materials, partial results, or internal data must be wiped clean from memory immediately after use. This is mandatory to prevent memory-based side channel attacks where an adversary analyzes memory remnants, registers, or cache lines to extract the session key or private key components. Next, we enforce mathematical purity. The implementation must use integer arithmetic only and floating point math is banned. Floating point operation can introduce small measurable differences in execution line or rounding, which are highly dependent on the underlying CPU architecture. These variations can create a side channel vulnerability. Using only integers guarantees deterministic, consistent, and predictable results across all compliant hardware platforms. Finally, we have the integrity gate, input validation. The implementation must include mandatory checks on all inputs to the encapsulation and decapsulation functions. This ensures that the shared secret key, the ciphertext, and the public key conform to the exact expected structure and length. This is a necessary defense against common exploitation techniques that use malformed inputs to induce errors, crash the system, or disrupt the decapsulation process to potentially leak information. Next up is FIPS 204. If FIPS 203 gave us our secure key exchange with ML-KEM, FIPS 204 gives us our digital signature standard. This is the new quantum safe way to guarantee trust and identity in digital transactions. Let's move on to FIPS 204. If FIPS 203 defined our key exchange mechanism, FIPS 204 defines our digital signature standard that is vital for trust and identity. FIPS 204 introduces the ML-DSA algorithm, the module lattice-based digital signature algorithm. Its purpose is clear: to be the designated high-performance replacement for all legacy digital signature algorithms, including RSA and ECC, which are no longer safe in the face of quantum computing. The algorithm is founded once again on lattice-based cryptography. The design choice ensures that ML-DSA can perform the necessary signing operations with speed and efficiency compared to or even exceeding current classical systems. The standard outlines the three foundational steps for any signature scheme: key generation, signature creation, and signature verification. These processes guarantee the secure authentication of the signer and the integrity verification of the digital message, meaning the data hasn't been tampered with. Crucially, ML-DSA's standard signing method is head signing, meaning it incorporates both a secret key and a secure, unique random element to enhance security and prevent leakage. For deployment flexibility, ML-DSA offers three distinct security levels: ML-DSA 44, ML-DSA 65, and ML-DSA 87. These tiers allow organizations to carefully manage the trade-off between performance overhead and security strength. For instance, higher tiers mean slightly larger keys and signatures but provide maximum assurance for high-value assets. Adopting FIPS 204 is a key strategic priority. The standard provides comprehensive implementation guidelines that are crucial for developers, ensuring that all conforming systems can interoperate smoothly. This is essential for a universal rollout across the PKI environment. This standard also allows for pre-hash signatures known as hash ML-DSA. This option lets organizations efficiently sign a short digest or hash of a large file rather than the entire file, which is common in many current digital signing workflows. Additionally, performance analysis shows that ML-DSA is exceptionally well suited for high volume environments like code signing and certificate issuing. By adopting this standard, organizations are not only achieving quantum resistance, but are also taking a proactive, necessary step to ensure long term regulatory compliance in the digital security domain. Now, let's focus on the ingenious design philosophy of ML-DSA. The algorithm strength doesn't come from a single complex idea. It comes from six core principles built into its structure, making it robust, reliable, and fundamentally testable in any environment. First, let's discuss the external internal split. This is the foundational architectural rule. Every core function, which is key generation, signing, verification, is cleanly divided. The external component is the security wrapper. It handles the non-deterministic actions, generating randomness, accepting the message, and running initial validation checks. The internal component is the pure math engine. It's entirely deterministic. The same input always produces the same output. This separation is crucial for compliance as it allows auditors to focus validation entirely on the predictable, unvarying mathematical code. Next, we look at key generation and seed secrecy. The process ensures maximum secrecy right from the start. Key generation requires no user input. The algorithm simply calls upon a NIST approved random bit generator to create a highly secure 256-bit seed. This seed is the single source of entropy, guaranteeing that the key's security is derived from high quality randomness. Next, let's consider the two signing modes. The default is hedge signing, which is the gold standard for security. Hedge means we add a fresh random layer to every single signature. The system generates a fresh 32-byte seed for every signature and mixes it into the process. This acts as a powerful defense shield, jumping the internal state to protect against sophisticated side channel attacks that try to reduce the private key. The alternative is deterministic signing. This option mode eliminates randomness, fixing the seed to a 32-bit string of zeros. The result is a fully deterministic process. Signing the same message twice always yields the same signature. This predictability is invaluable for rigorous testing, debugging environments, and compliance where specific repeatable results are required. The final two principles govern the algorithm's integrity and efficiency. The rejection sampling tool is the core integrity check that runs during signing. The process attempts to create a signature component and then runs rapid internal validity checks. If a check fails, the signature is discarded and the system immediately loops with new randomness. The mechanism known as Fiat Schmidt with aborts mathematically guarantees that only valid signature schemes are ever released. Finally, we have pre-hash ML-DSA, the performance design feature. For every large messages, say a multi-gigabyte file, signing the entire data stream can be a major bottleneck. The hash ML-DSA variant solves this by allowing the application to first create a secure hash digest of the message. The signature is then computed only on the digest, significantly accelerating the signing operation without compromising the security strength of the overall operation. Just like ML-KEM, our primary digital signature algorithm ML-DSA comes with three approved parameter sets. This is where we make critical trade-offs between security, speed, and the size of the final signature. The names of these sets, ML-DSA 44, 65, and 87, are actually tied to the underlying dimensions of the math, but for us, they represent clear security levels. ML-DSA 44 gives us our baseline, aligning with security category 2, which is similar to AES 192 encryption. ML-DSA 65 steps up to category 3, Also AES 192 equivalent. This is the set that offers the best overall balance and is generally recommended for high volume use. ML-DSA 87 provides maximum assurance aligning with Category 5, which is equivalent to AES 256 encryption. This is your choice for the highest security requirements. When you choose a parameter set, you are directly affecting the storage and bandwidth cost of your signatures. As you move up the tiers, everything gets bigger. For example, the public key size nearly doubles as you move from the 44 set to the 87 set. Most importantly, the signature size itself increases significantly. Choosing the highest security ML-DSA 87 means you have a signature that is almost twice the size of the ML-DSA 44 signature. This means if you're doing constant high volume signing like a certificate authority, you have to balance that high security number against the increased storage needs and the network overhead for larger signatures. It's worth noting that algorithms gives us some flexibility on how we store the keys. While the default private key size can be quite large, if space is at a premium, we only need to store a small 32-bit byte C that can generate the rest of the private key on demand. If speed is everything, we can pre-calculate and store certain components to speed up the signing and verification process. Ultimately, your choice here is strategic. Higher security means larger data size, and ML-DSA 65 is the recommended workhorse for its strong balance. ML-DSA provides a clear and robust framework that offers tangible benefits for any business impacting your development processes, security, and performance. FIPS 204 was designed to make the transition to quantum safe signatures as smooth as possible for developers. The standard separates the algorithm's functions, providing a clean and well-defined interface. This allows developers to easily integrate ML-DSA without needing to understand the complex cryptographic internals. It's like getting a pre-assembled component, you just plug it and it works. By handling critical tasks like randomness and formatting in a controlled external layer, the design minimizes the chance of human error during implementation. This makes your cryptographic systems less prone to mistakes and more reliable. The comprehensive guideline is the standard that ensures that implementations are consistent. This guarantees interoperability, meaning your digital signatures will work seamlessly across different platforms and systems, whether you're signing software updates or securing a document. Adopting FIPS 204 is a strategic move that provides a powerful layer of security and ensures compliance with critical regulations. This is the core purpose of FIPS 204. By adopting it now, you ensure that your digital communication and data, from legal documents to financial transactions, will be secure against attacks from future quantum computers. As a FIPS standard, ML-DSA is mandatory for US government agencies and their contractors. Implementing it ensures you meet these regulatory requirements and can continue to do business with the public sector. The deterministic nature of the internal functions makes the system way more predictable and easier to test. This simplifies the auditing of your cryptographic implementations, allowing you to easily prove they are secure and compliant. ML-DSA provides a great balance of strong security and high performance with options to fit different business requirements. The standard's use of advanced algorithms like the number theoretic transform or NTT dramatically speeds up signature creation and verification. This means you get robust security without sacrificing the speed and efficiency your business requires. The standard includes an optional pre-hash ML-DSA feature. This provides flexibility to optimize performance for various use cases, especially when you need to sign very large files or when you have limited hardware resources. FIPS 204 allows for different trade-offs in key and signature sizes with its 3 security levels, enabling you to choose the best balance of performance and security for your specific requirements. ML-DSA is our main digital signature and it's incredibly fast. But to make it secure for the quantum era, the builders, the engineers writing the code must follow these 6 implementation requirements. These requirements are all about closing the tiny, sneaky security gaps that hackers exploit. The stopwatch rule or the constant time execution is the most critical requirement. Don't let the time it takes to run your code leak the secret key. When the program is multiplying those secret lattice polynomials, it has to take exactly the same number of clock cycles every single time. It doesn't matter if the secret value is a small number or a huge number. The clock time must be constant. This defeats timing attacks, which are a hacker's most common tool against fast math. The purest randomness mandate. Everything begins with randomness. Every secret component of the key and every random toss of the dice during the signing process must come from a source that NIST has selected. We're talking about high assurance random bit generators. If you're building for the highest security level, your random source needs to be top tier. The instant erase policy or zeroization to avoid leaving any crumbs behind. The second the program is done with a piece of sensitive data, whether it's the private key itself or just a temporary vector, it must be immediately scrubbed from the memory. This is called zeroization. It's like having a whiteboard that gets instantly wiped clean, preventing a hacker from peering into the machine's memory to find secrets that were supposed to be temporary. ML-DSA sometimes has to reject a random signature attempt and try again, a process that takes varying amounts of time. The rule here is simple. This variation in time cannot, under any circumstances, hint at the secret key. The code must be engineered so that only public non-secret data controls the timing of those restarts. This is a subtle but important defense against making the secret key guessable through timing analysis. Engineers must use only whole numbers or integers for all cryptographic math. Floating point numbers are strictly forbidden. Why? Because different computer chips handle floating point math differently, leading to small, unpredictable timing variations. Using only integers guarantees perfect, predictable, and consistent results across every certified device, removing another potential source of security leakage. The final rule is about boundaries. The ML-DSA code must be sealed off from the rest of the application. It has to be a black box. The application can ask it to sign a document, but it can never reach inside and touch the private key or manipulate the internal calculations. The module must handle its own secure randomness and its own key management, ensuring the entire process is self contained and tamper proof. That's all for part 1 of the series. We will be discussing the remaining algorithms in our next video, so stay tuned and stay secure.